In August of 2012, a team of scientists at NASA was staring at a stream of numbers coming from a spacecraft 15 billion miles away, and none of them could agree on what they were looking at. Voyager 1 had just done something no human-made object had ever done before. Every other measurement coming back from the spacecraft said it had left the solar system entirely. The density of charged particles around it had jumped dramatically. Cosmic rays from the wider galaxy were flooding in. By every reasonable definition, Voyager 1 should have just crossed into interstellar space. But one single measurement refused to cooperate, and it was enough to make some of the most experienced scientists in the field hesitate to announce the most significant space discovery in decades. The direction of the magnetic field around the spacecraft had not changed, not even a little. And more than a decade later, after a second spacecraft crossed the exact same kind of boundary in a completely different part of the sky and found the exact same impossible result, scientists still do not have a fully settled explanation for why. This is the story of the invisible wall at the edge of our solar system, the one boundary that both Voyager spacecraft have now crossed, and the strange magnetic mystery neither crossing was able to fully solve. To understand why this matters, you first need to understand what scientists expected to happen, because the prediction itself was simple, logical, and, as it turned out, wrong in a way nobody was prepared for. Our entire solar system sits inside an enormous bubble called the heliosphere, inflated by the constant outward pressure of the solar wind, a stream of charged particles blasting outward from the sun in every direction. That solar wind carries the sun's own magnetic field along with it, stretched out into a long spiral shape as the sun rotates, a structure scientists call the Parker spiral, named after the physicist who first described it. Inside the heliosphere, this solar magnetic field dominates everything. It shapes the environment around every planet, including Earth. But the heliosphere does not extend forever. Eventually, the outward push of the solar wind gets overwhelmed by the pressure of the interstellar medium, the thin material drifting in the space between stars, and the solar wind's dominance ends at a boundary called the heliopause. Cross that boundary, and you leave the sun's magnetic influence behind entirely, entering a region governed instead by the galaxy's own magnetic field, a field with an origin, a history, and a direction that has nothing at all to do with our sun. Because these two magnetic fields come from completely different sources, one from a single star and one from the wider galaxy, scientists had every reason to expect they would point in noticeably different directions. That expected change in direction was supposed to be one of the clearest, most unambiguous signs that a spacecraft had truly left the solar system. Cross the heliopause, and the magnetic field should visibly swing around to a new orientation, like a compass needle suddenly discovering a completely different magnetic north. Voyager 1 reached that boundary first. Launched in September 1977, it spent decades flying past Jupiter and Saturn before heading up out of the plane of the planets, aimed squarely at the edge of the solar system. On December 16, 2004, at a distance of about 94 astronomical units from the Sun, it crossed something called the termination shock, the point where the solar wind abruptly slows from a supersonic speed to a subsonic one, marking the inner edge of a thick transitional zone called the heliosheath. Then, on August 25, 2012, at roughly 121, 6 astronomical units from the Sun, Voyager 1 finally reached the heliopause itself. The plasma data told a clear story. The density of charged particles around the spacecraft jumped sharply, exactly as predicted for a genuine crossing into interstellar space. But there was a serious complication. Voyager 1's primary plasma instrument had failed decades earlier, back in 1980, shortly after its Saturn flyby, meaning scientists had to rely on other indirect methods to confirm what the plasma environment actually looked like. And the one instrument that was still working perfectly, the magnetometer, was reporting something that made almost no sense at all. The direction of the magnetic field around Voyager 1 had barely moved. Scientists had expected a dramatic swing, tens of degrees, marking the clear transition from the Sun's Parker spiral into the galaxy's own separate magnetic field. Instead, the field's direction stayed almost exactly the same, on both sides of a boundary that was supposed to separate two completely independent magnetic systems. This single discrepancy delayed the confirmation of one of the most important milestones in the history of space exploration. For months, some researchers proposed that Voyager 1 had not actually left the solar system at all and was instead passing through some undiscovered internal structure, still technically inside the heliosphere. Others suggested the true heliopause might sit much farther out than anyone had calculated. It was only once the plasma density data became truly overwhelming, alongside a spike in high-energy cosmic rays arriving from the galaxy, that NASA felt confident enough to formally announce that Voyager 1 had crossed the heliopause and entered interstellar space. But the magnetic field puzzle itself was never actually solved. It was simply set aside, acknowledged as strange, while the rest of the evidence carried the announcement forward. For years, there was a reasonable possibility that this was simply a fluke, a one-time coincidence tied to Voyager 1's specific location and trajectory. With only one data point, nobody could be entirely sure whether this bizarre alignment was a genuine feature of the boundary itself, or just an unlucky accident of geometry, a chance alignment that happened to occur exactly where Voyager 1 crossed and nowhere else. Then Voyager 2 arrived at the same kind of boundary, and any hope of writing this off as a coincidence disappeared. Voyager 2 followed an entirely different path through the solar system, launched 16 days before its twin, but sent on a slower trajectory that took it past Uranus and Neptune, missions Voyager 1 never attempted. It crossed its own termination shock on August 30th, 2007, at about 84 astronomical units, then continued outward. For another 11 years before finally reaching its own Heliopause crossing, on November 5th, 2018, at a distance of about 119 astronomical units, in a completely different region of the sky than where Voyager 1 had crossed 6 years earlier, at a different latitude, a different longitude, an entirely separate slice of the boundary surrounding our solar system. If Voyager 1's strange magnetic alignment had been a coincidence, Voyager 2 should have shown something different. It did not. NASA's own announcement described the result plainly. Voyager 2's magnetic field instrument confirmed the same surprising pattern Voyager 1 had reported years earlier. The magnetic field just beyond the heliopause was parallel to the magnetic field found just inside it. Two spacecraft, launched the same year, traveling in completely different directions, crossing the boundary between our solar system and the galaxy at completely different points in space and time, both found the same impossible-seeming result. The magnetic field simply did not rotate the way basic physics predicted it should. That is the invisible wall referenced in this story's title. Not a physical barrier you could touch or see, but a genuine, measurable, repeated anomaly at the exact edge of our solar system, one that has now been independently confirmed twice, in two different locations, using two different spacecraft. Scientists have not been sitting idle in the years since. Several serious explanations have been proposed, and each one captures part of the picture without fully resolving it. One leading idea treats the interstellar magnetic field almost like a stretched piece of fabric draped over an obstacle. Picture the heliosphere as a giant beach ball sitting in the way of the surrounding interstellar magnetic field, which was originally flowing in some other direction entirely before it ever encountered our solar system. As that field flows around the heliosphere's outer surface, it gets physically deflected, bent, and dragged along the boundary's shape, similar to how water flowing around a rock gets pushed into new directions near the rock's surface, even though the water was originally flowing in a single, consistent direction elsewhere. Researchers led by Nathan Schwadron at the University of New Hampshire published a study using this exact idea, reanalyzing Voyager 1's magnetic field data and finding that its measured direction had been slowly rotating, little by little. Ever since the spacecraft first crossed into interstellar space, evidence consistent with the field still being deflected by its proximity to the heliopause, rather than measuring the true, undisturbed direction of the wider galactic field. That is a genuinely compelling piece of the puzzle, but it comes with its own unresolved complication. Even using this deflection model, Voyager 1's measured magnetic field direction still came out more than 40 degrees off from the direction other independent measurements suggested the true interstellar field should point, based on data from NASA's Interstellar Boundary Explorer, a separate spacecraft that studies the boundary of the heliosphere from a very different vantage point, orbiting much closer to Earth. That mission detected something called the Ibex ribbon in 2009, a bright, curving arc of energetic particles wrapping around a portion of the sky, believed by many researchers to trace the true direction of the pristine, undisturbed interstellar magnetic field. If the deflection model were the complete answer, Voyager 1's measurements should eventually line up with that ribbon's predicted direction as the draping effect fades with distance. Instead, a substantial gap has remained. A separate team of researchers took a different approach entirely, proposing that Voyager 1's specific measurement could be explained by simple geometric coincidence. Both Voyager 1's crossing point and the Ibex ribbon's center happened to sit at a similar heliolatitude, close enough in the sky that their directions would naturally appear similar, even if the underlying fields were not actually connected in any deeper physical way. That same research team went further, making an actual testable prediction ahead of time. If their explanation were correct, they argued, Voyager 2 should show a noticeably larger difference between its inner and outer magnetic field directions than Voyager 1 did, since Voyager 2's crossing point sits at a meaningfully different latitude and longitude than Voyager 1's. That is exactly the kind of prediction good science is supposed to make. A clear, specific forecast that could later be checked against real data. And when Voyager 2 actually crossed the Heliopause years later, the result did not match the prediction. NASA's own description of the Voyager 2 crossing stated plainly that the field was parallel across the boundary, essentially the same striking alignment Voyager 1 had already shown, not the larger predicted difference. The geometric coincidence explanation, at least in its original form, did not hold up against the second data point it was specifically designed to test. By 2020, researchers studying both sets of data together noticed something even stranger sitting underneath the basic alignment puzzle. Rather than the magnetic field abruptly snapping into a new direction right at the heliopause, both spacecraft recorded something closer to a slow, smooth, gradual rotation, beginning well before the actual boundary crossing and continuing steadily afterward, as if the field were easing into its new orientation across a wide transition zone rather than switching cleanly at one specific line. Even stranger, the angle of that gradual rotation, in both cases, ended up surprisingly close to the angle predicted by the Parker spiral, the mathematical description of the Sun's own magnetic field structure. That similarity is genuinely puzzling because there is no obvious physical reason the truly separate independent interstellar magnetic field should happen to align with a mathematical pattern that describes our own Sun's magnetic behavior specifically. It would be a bit like discovering that the wind patterns on the far side of a mountain range happen to trace the exact same shape as the valley on the near side, despite there being no obvious reason for the two to be connected at all. As recently as October 2025, this exact puzzle was still being actively discussed in scientific literature, described in one detailed article as the confounding magnetic readings of Voyager 1, a phrase that captures the situation about as honestly as possible. Voyager 1 remains humanity's very first direct beacon in interstellar space, meaning every other clue scientists have about the true direction of the undisturbed interstellar magnetic field comes from indirect methods. The ibex ribbon, the polarization of starlight passing through the local interstellar medium, and subtle patterns in how cosmic rays arrive from different directions in the sky. None of these indirect methods perfectly agrees with each other, let alone with what the two Voyagers actually measured directly, on location, with real instruments physically present in the region being studied. That is the genuinely uncomfortable truth sitting at the center of this entire mystery. We have exactly two direct physical samples of the magnetic field just beyond our solar system's boundary, gathered by two aging spacecraft built in the 1970s, and both samples show the same strange, unexpected alignment with the Sun's own magnetic field, an alignment that multiple competing theories have each tried and partially failed to fully explain. The draping model captures part of the story but leaves a 40-degree gap unaccounted for. The geometric coincidence model made a specific, testable prediction that the second spacecraft's data did not confirm. The gradual rotation pattern reveals a smoother transition than anyone initially expected, but does not, by itself, explain why that transition happens, to trace an angle so similar to our own Sun's magnetic spiral. Every one of these partial explanations agrees on one thing. This is not simply a mistake, a broken instrument, or a data processing error. Both magnetometers involved have been tested, cross-checked, and confirmed to be functioning correctly across nearly 5 decades of continuous operation. The anomaly is real. It has been independently measured twice in 2 different regions of the sky, using 2 separate spacecraft built from the same design. What remains unresolved is not whether the effect exists, but exactly why it exists, and what it ultimately reveals about the true structure of the magnetic field surrounding our entire solar system. It is also worth remembering just how much rode on this single measurement back in 2012, and how differently the story of Voyager 1's historic crossing could have unfolded. Confirming that a spacecraft had genuinely left the solar system for the first time in human history was never going to rest on a single number. NASA ultimately built its case on multiple independent lines of evidence: the sharp rise in plasma density, the flood of incoming galactic cosmic rays, and the steady behavior of the magnetic field's strength itself, even though its direction refused to cooperate. Had the magnetic field been the only piece of evidence available, the announcement might have been delayed for years, or the crossing might have been misidentified entirely. Instead, scientists were forced to make a judgment call. Treat the stubborn magnetic field reading as a genuine anomaly worth investigating further, rather than proof that the spacecraft had not actually crossed the boundary at all. That judgment turned out to be correct, but it left behind exactly the kind of loose thread that has kept researchers occupied ever since. There is something worth sitting with in the fact that This particular mystery cannot simply be solved by building a better telescope or running a more powerful computer simulation from the comfort of Earth. It requires an actual spacecraft, physically present at the boundary itself, taking real measurements in a region no telescope can properly observe from a distance. Right now, exactly 2 machines in all of human history have ever been in a position to gather that kind of direct evidence, and both of them are approaching the end of their operational lives, losing roughly 4 watts of power every single year, as their nuclear power sources continue their slow, irreversible decay. Neither spacecraft can be repaired, neither can be replaced quickly. Any future mission capable of reaching a comparable distance would take decades to design, build, launch, and travel far enough to matter. And in the meantime, humanity's only 2 direct witnesses to this exact puzzle are slowly, quietly running out of time. It is worth remembering just how strange the IBEX ribbon itself remains, since so much of this mystery depends on using it as a stand-in for the true interstellar magnetic field direction. When NASA's Interstellar Boundary Explorer first detected that glowing arc of energetic particles in 2009, wrapping unexpectedly across a wide swath of sky, nobody had predicted anything like it beforehand. No existing model of the heliosphere anticipated a ribbon-shaped structure at all, and years after its discovery, researchers still do not fully agree on the exact physical mechanism producing it, only that it appears connected in some way to the direction of the surrounding interstellar magnetic field. Using an unexplained ribbon to help explain an unexplained magnetic field alignment is a bit like trying to solve one riddle by comparing it to a second, only partially related riddle. It helps narrow the possibilities, but it does not hand scientists a clean, final answer. This is also why serious proposals exist within NASA and the broader heliophysics community for a dedicated interstellar probe, a hypothetical future mission specifically designed to travel beyond the Heliopause carrying modern instruments built from the ground up to study exactly this kind of question, rather than repurposing hardware originally designed in the 1970s for a very different mission to the outer planets. Such a probe could carry multiple working plasma instruments, redundant magnetometers, and dedicated sensors for measuring the interstellar magnetic field directly, without needing to rely on indirect inference the way Voyager 1 has been forced to since its own plasma instrument failed decades ago. But any such mission remains largely conceptual for now, competing for funding against many other priorities, and even in the most optimistic scenario, it would likely take several decades simply to reach the same distance the Voyagers already occupy today. Until then, the only 2 direct samples of this boundary humanity has, or will have for the foreseeable future, remain the ones already sitting in the data both Voyagers sent home years ago, still being pored over, reanalyzed, and argued about by researchers determined to finally make sense of them. That is what makes this particular unsolved mystery different from most others in astronomy. It is not a distant phenomenon we can simply keep observing patiently from Earth, whenever convenient, using ever-improving instruments over the coming decades. It is tied directly to 2 very specific, very fragile machines, both already well past their expected lifespans, both still sending back data that nothing else in existence can currently replicate. Every additional measurement either spacecraft manages to send home adds another small piece to a puzzle that has already resisted a complete explanation for well over a decade. For now, the honest answer remains exactly what it has been since 2012. Scientists know precisely what they observed. They have several partial, genuinely useful explanations that each capture part of the picture, and they still do not have one single, fully agreed upon answer for why the boundary of our entire solar system behaves this way. The magnetic field that was supposed to mark a clean, obvious transition from our sun's influence to the wider galaxy instead revealed something stranger, an invisible wall that 2 separate machines, launched the same year but traveling in entirely different directions, both quietly walked straight through without ever fully explaining what was actually happening as they crossed it. Somewhere out there right now, both Voyager spacecraft continue transmitting whatever data their remaining instruments can still gather, adding new information to a mystery that has already outlasted most of the scientists who first noticed it. Nobody currently knows for certain when, or even if, this particular question will ever be fully answered. But every signal that still manages to cross the billions of miles back to Earth is another chance that the next data point finally reveals what has been hiding in plain sight at the edge of our solar system all along. If you want more real, unresolved mysteries from the true edge of what science actually understands about our solar system, subscribe and stay with us, because this particular wall is still out there, and nobody has fully explained why it exists.